This video is about normality tests and how to transform skewed data to a normal distribution. Statistical hypothesis tests are used to see if two groups of things are the same. The more powerful tests, like the student's t-test and ANOVA, require a normal distribution of data. If the data are skewed, they can be transformed to normal using a powerful function such as the Box-Cox method. In this Jupyter Notebook, we'll look at different methods for testing for normality and, if needed, transforming the data to a normal distribution using a power normal function, namely the Box-Cox method. Testing a distribution for normality can be accomplished in at least three ways. The first way is the visual graphic inspection of the data. Do histograms and PDFs have a symmetrical bell shape? A box and whisker plot can also be looked at, but mainly sees symmetry. And then a more powerful method is the quantile plots, which look for linearity of the data against z-scores of the observed data and a standard normal theoretical distribution. Another method is to look at descriptive statistics. Are the mean, the median, and the mode, or the central tendency of the data the same, and also looking for skewness and kurtosis being small values. And then there are a series of numeric normality tests, such as the Shapiro-Wilks test, which can also be used to test for normality. We'll look at the caveats in these methods. David Box and George Cox developed a method in 1964 which uses an exponent lambda to transform the skewed distribution to normal. Here are the formulas that they proposed. So we'll implement this as well. There's also another video I've made on p-values in the Jupyter Notebook, which is basically how you determine if a distribution is the same as the normal distribution. Now, let's take a look through the Jupyter Notebook. In the first cell, we import the libraries we'll need for doing the Python analyses. Then we'll create some distributions to test for normality. I suggest using these values for a min, most likely, or mode and max value to create these distributions for normal, skewed and strongly skewed, and log normal. And down below here in the next cell, you can see I'm initiating these values with a minimum of 25, 250, and 1650, which is the log normal distribution. And we're going to take 1,000 samples, random samples, from the distribution to check for normality. And we're going to use a lambda of 10. Lambda is a function in the beta distribution that allows you to control the dispersion. And the next cell is a function that I've written to do descriptive statistics. Here we just talk a little bit about the beta distribution and the use of lambda to control the distribution, and we assign two shape factors. And here I'm pointing out that alpha, beta, loc, and scale are the key parameters for doing the beta distribution. So let's make a beta distribution for that log normal distribution we talked about. Here's where I'm making the distribution. And here I make a normal distribution to test against. So we can plot them together. And we plot them together. And the red is the beta distribution, which approximates a log normal, and a normal distribution. And here are the descriptive statistics for the log normal distribution. And here you could see that the mean and the median are different, as well as the median, which is the p50. Now we can look at the log normal distribution as a comparison to that beta that we created. Here's the syntax for the log normal distribution. And if you don't have data to fit a log normal distribution, I found that it's easiest to create a beta distribution and then extract those parameters. So here we go. Here we're going to extract the shape, loc, scale that we need for a log normal distribution, but we're extracting it from these b-vals, or the beta distribution values. And then here we create the log normal values from the shape, loc, and scale. And then in these two lines of code here, we create the x and y values we need for plotting the PDF of the log normal distribution. So let's go down, let's take a look at the beta and log normal distributions. In red is the log normal, which has a much longer tail, and the beta. One of the key differences between a log normal distribution and a beta distribution is the log normal is unbounded and theoretically can go on forever. The beta distribution is bounded, so it is restricted to those values that we gave it, around 60, 250, and 1650. And you can see that the log normal does not quite honor all those values. But they are statistically similar given the number of orders of magnitude of the data that they span. Now we'll take a look at transforming the data. In the previous cells, we've created a normal distribution, which would be the n-vals. We've created a beta distribution, which are the b-vals, and we created a log normal distribution, which are the ln-vals. So here we can decide what we want to transform to normal. And I've selected the beta values, or b-vals. You can't have negative values in a log normal distribution, so we have to have a little bit of code here to trick it into not having negative values if they occur. Here's where we actually do the Box-Cox transformation, and it's easy as just saying Box-Cox equal and then the data that you want to use. The QQ plot that we use for looking at to see if the distribution is normal can be done as easily as just calling the SciPy stats library probplot and running it, and then just doing pylab.show, and that will do it. But I wanted to do things a little bit differently. So what I'm doing is I'm running the probplot routine, but I'm writing out the arrays that I use to get the points and the linear fit. So I've done that here, and I've done it for the raw data, the b-vals, and here I've done it for the transform data that we got from the Box-Cox transformation. And now I'm just going to do some plotting of histograms and PDFs of the raw data and the QQ plots. So here we look at the original data. So this is the beta distribution, and you can see that it's strongly skewed. And when we look at the QQ plot, here's the linear fit. If it's normal, the observed data will plot along the blue line, and that would tell you that it's normal. And over here we have the transform data. This is the Box-Cox power function, lambda is 0.3378, and we can see we get something that looks like a bell-shaped curve. And when we look at the QQ plot, it largely fits on the linear except for the tail, which is not unusual when sampling a normal distribution at large z values. So here this is occurring out beyond 2.5 z values. So I would say this was normal. Here we just compare some of the descriptive statistics to convince ourselves that the mean, the median, and the P50 look good, and the skew and the kurtosis are both very small numbers. So this transform distribution would qualify as a normal distribution based on the QQ plot. Now let's move on to normality tests. While there are a number of normality tests, they don't always provide the same result. Just because a distribution, especially a bounded distribution, may be symmetrical, it is not necessarily normal. In the following cell, we'll examine 6 statistical normality tests, plus visual inspection of charts and descriptive statistics. I want to note that normality tests are sensitive to the sample size, among other factors. In the cell below, vary the number of samples. Try 50 samples, then try 5,000. Also, there are 8 different distributions to choose from. So let's play around with some of these distributions and sample sizes and see what kind of results we'll get. For our first experiment, let's choose a normal distribution. So we'll come over here. Here's the normal distribution. And we'll try it with 5,000 samples. Over here is a description of the different data sets and distributions that are available to try in this cell. So we'll move down, and the histogram looks normal, the PDF looks normal, the QQ plot is quite linear, it looks normal, and here are the results of these different statistical normality tests. The Shapiro-Wilks says it's probably Gaussian. Anderson-Darling has a mixed result. The chi-square says it's not Gaussian, but in my opinion, these unbinned chi-square tests are unreliable, so I would ignore these. The Kolomogrov-Smirnov test says probably Gaussian. Lilly-Fors, probably Gaussian. Diagnosto, probably Gaussian. Jacques-Berra, probably Gaussian. And the descriptive statistics, it has a mean of about 100, a median of about 100. The P50 is about 100, so the central tendency looks the same. And the skew and kurtosis are also quite small. So this looks to be normal overall. Now let's change the number of samples to 50. So we scroll up, change this to 50, and run it. And let's come down and take a look. Well, the histogram doesn't look particularly normal because of the small sample size. The QQ plot looks quite linear. Shapiro-Wilks says it's probably Gaussian. Anderson-Darling says it's Gaussian. And it looks like all the tests look Gaussian. The mean, the median, and the P50 look about the same. And again, skewness and kurtosis looks small. So it seems to be working with these small sample sizes. Now let's change our data set. And we'll go with a symmetrical beta with alpha and beta equal 3. So this is approximately about the same distribution as a triangle distribution. Hit return, and we're with 50 samples. And doesn't look particularly normal. QQ plot looks okay. Gaussian, 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 Gaussian. Statistics, the mean, the median are a bit different. As well as the P50. The skewedness looks a little high. And the kurtosis looks a little high, quite small, in fact. So it has kind of a broad distribution. So I'm not quite sure this is normal. Let's change the sample size now to 5,000 and see what happens. Looks normal. We can see the tails out here beyond around 2 standard deviations are tailing off from the straight line. And not Gaussian, not Gaussian. Chi-square says it's probably Gaussian. Not Gaussian, not Gaussian, not Gaussian, not Gaussian. The mean, the median, and the P50 are quite similar. It's very symmetrical. The kurtosis is a little bit on the small side. It's not really skewed. So in the strictest sense, it's not normal, but it looks normal. So depending on what your criteria is for the types of hypothesis tests that you're going to run, you may find this to be not adequate. Let's try one more data set. This time we'll try a skewed beta distribution. So here's the skewed beta distribution, and we'll run it. And clearly it's skewed, And you can really see the tail over here coming off the QQ plot. So this doesn't look normal. This says not Gaussian, not Gaussian. See, the chi-square says it's Gaussian. This is why I suspect that chi-square is not working well with Python's built-in chi-squared function. Not normal, not normal, not normal, not normal. And clearly the descriptive statistics are indicating that it is not normal. One thing I want to point out here, when you look at the range of z-values with 5,000 samples, we're getting out almost to 4 standard deviations. So I want to run this at 50 now and see what happens, and pay attention to the number of standard deviations on the QQ plot. Let's run it here at 50. Does not look normal. It kind of fits. Not normal. You get mixed results from the Anderson-Darling. Chi-squared says probably Gaussian. I don't know. Kolomogrov says it's probably Gaussian. Probably Gaussian. Probably Gaussian. So at small samples, it has a hard time determining whether it's really normal or not, but you're only going out to 2 standard deviations. And what we saw before was the big deviations from the linear trend were occurring after about 2 standard deviations on either side. So that is the issue here. And I should also mention that if I run this several times, you get a different looking plot because you're sampling randomly. So sample size is particularly important to doing these types of analyses. As I had mentioned earlier, the chi-squared distribution with the default function in Python doesn't seem to do an adequate job. So I've written a script that bins the data and then does the chi-squared analysis. And here's the script. And here's a solution for the same data we saw above with 50 samples. And it tells us that it's probably Gaussian. And what the script does basically is it looks at the bin data and it looks at the frequency in each bin. And then it looks at what the expected frequency would be for the chi-squared. The difference between the expected and the frequency, or the expected and the observed, is the difference, and the sum of these differences represents the chi-squared statistic. And then we run the p-value on this, and then if we see a p-value smaller than 0.05, then it would not be normal. But here the p-value is greater than 0.05, so it's probably Gaussian. Let's redo this analysis, but let's change the number of samples to 5,000. And it should say that it's not Gaussian. Let's go down. Okay, so the beta distribution looks symmetrical, but the p-value is very small, so it's probably not Gaussian. And as we saw before, with these bounded distributions and large numbers of samples on the QQ plot, the tails deviate from the linear trend. So that is the binned chi-squared analysis. I thought it'd be interesting just to take a closer look and to see what it looks like. Basically, the chi-squared distribution is a variation of a right-tailed gamma distribution, where its shape factor is the degrees of freedom. So here's a script that plots up the chi-squared distribution for the data we were just looking at. Here we can see in red is the chi-squared distribution, the area shaded in red. This is the area with a p-value less than 0.05, or that critical value. And there's a reference line. And I've also put on here the cumulative probability distribution function here, which goes to 1. So as long as our data point falls to the left of this reference line, we have a normal distribution. What I want to do is change this so you can see what it looks like when it's not a normal distribution. So I'm going to go up above and we'll change to a skewed distribution and make it 500 samples. Here's the skewed distribution. We'll take off the comment. We'll run it. We'll come down below. Probably not normal. And let's take a look at this chi-squared distribution. And as you can see, for our asymmetric distribution, it has a p-value basically of 0. And you can see that it's not a normal distribution. Let's take a look at the effect of sample size on the outcome of the analysis of whether it's normal or not. I've run a Monte-Carlo sensitivity for a beta distribution that's symmetrical, that roughly has the shape of a triangle distribution, so a fairly broad standard deviation. And we're going to run a sample size of 50 and do 1,000 trials. So let's run this, and let's take a look at the result here. We can see it doesn't look particularly normal. And from these trials, we saw we had a minimum p-value of 0.001 and a maximum p-value of almost 1. And when we look at this, it says that 85% of the trials were successful, or 852 trials out of 1,000 produced a normal distribution. Let's go up and change the sample size now, and let's try 500. Come down. It's starting to look normal. And here, 411 out of 1,000 trials produced a normal distribution, or 41%. This is the effect of the random sampling. Let's try it now at 1,000. Scroll down. Looking normal. And now it says that only 94 of the 1,000 trials were successful or normal, because now it's starting to see that the tails are not normal out in that area of z-values above about 2.5. And let's do one last trial at 5,000. Scroll down. Looks normal, but 0 of the trials were successful. So the bottom line here is that when we have things that are symmetrical and small numbers of samples, the chi-squared will produce a normal finding of the distribution, whereas if we increase the samples high enough to sample out at the tails, we'll find that these distributions are not normal. In this last cell, we're going to try the Kolomogrov-Smirnov 2 sample test. This basically compares two distributions to see if they're the same. We're going to start off looking at a beta distribution with a lambda of 10, which makes it almost normal, and a sample size of 50. And we're going to compare it to a normal distribution and see what the results are. And here we can see the beta distribution is the red histogram and the normal is the blue. And over on the right, we can look at the PDFs. But the test says that they're probably the same distribution. So let's play with this a bit. Let's change this to 5,000 samples and see what we get. It says it's probably not the same distribution, and you can pretty much see that here. Let's try a different lambda. So let's make this 3. So this is going to make it more like a triangle distribution. Return. They're probably not the same, but you can see that their standard deviation is roughly the same, similar, but the Kolomogrov-Smirnov test value says that they're not the same. Let's try this now at 50 samples and see what we get. The PDFs still look about the same. The histograms have more or less the same shape, and it says it's probably the same distribution. So this is just another example showing that sample size has a strong effect on normality tests. I hope you found this video helpful, and thank you for watching.